All right, let's talk about something that trips almost everyone up, the difference between speed and velocity. I know. You probably use those words to mean the same thing every single day. But by the end of this, you're going to see why in the world of physics, they are absolutely not the same thing.
So, picture this. You're driving down the highway, you look down at the dashboard, and the needle is pointing straight at 100 kilometers per hour. You might say, wow, our velocity is 100, or we're going at a pretty good speed. We swap them all the time, right? But which one is actually technically correct? And look, for everyday conversation, it's totally fine. No one's going to call the physics police on you. But when we want to be precise, when we're talking science and really describing how things move, that little difference becomes absolutely crucial. It's one of those fundamental ideas you have to get right.
So here's how we're going to break this all down. First, we'll look at the two basic ways we measure things, which is really the key to this whole puzzle. Then we'll see how that applies to the path you take versus, say, the shortcut between 2 points. And finally, that'll lead us right to the main event, the final showdown between speed and velocity. Okay, let's get right into the heart of it. The entire difference, and I mean the entire difference between speed and velocity comes down to one simple concept: scalars versus vectors. You get this, and I promise, everything else just clicks into place. First up, we've got scalars. Now, a scalar is about as simple as a measurement gets. It just tells you how much of something there is. That's it. It's just a number. Like it's 20 degrees Celsius outside, or this bag of sugar weighs 2 kilograms. It's just a value, plain and simple. And then you've got its counterpart, the vector. A vector is a little more sophisticated. It gives you the how much, the magnitude, but it also tells you which way, the direction. A great way to think about a vector is just as an arrow. The arrow's length tells you how big it is, and the way it's pointing tells you its direction. So let's put them side by side. A scalar is just a number. Magnitude only. 5 kilograms. Easy. A vector, on the other hand, has both. It has magnitude plus direction. So you're not just pushing with a force of 5 newtons, you're pushing with a force of 5 newtons downwards. That one extra piece of information, direction, is the game changer. So that's the theory. But how does this whole scalar versus vector thing actually play out in the real world? Well, let's apply it to something we can all visualize: movement. Let's imagine a little delivery drone. It takes off from its warehouse, flies 7 kilometers due east to make its first drop, and then it turns 90 degrees and flies 3 kilometers due north for its second stop. Pretty simple journey, right? Now, if we wanted to know how far that drone actually flew, we'd be talking about its distance. Distance is just the odometer reading. It's the total length of the path you covered. It doesn't care about turns or directions, it just adds everything up. And that makes it a scalar. So for our drone, this is super easy. It flew 7 kilometers and then it flew another 3 kilometers. You just add them together. The total distance it traveled is 10 kilometers. That's the total ground it covered on its little trip. But what if we don't care about the zigzagging path? What if we only care about where the drone ended up compared to where it started? Well, that's called displacement. It's the shortcut, the straight line from your start point to your end point. And because it's a straight line, it has a length and a direction. That makes it a vector. So for our drone, its displacement isn't 10 kilometers at all. If you draw a straight line from the warehouse to its final spot, that line is only about 7.6 kilometers long. And you have to include the direction, northeast. So see the difference? It traveled a distance of 10 kilometers, but its final displacement was 7.6 kilometers to the northeast. All right, with all that groundwork laid, knowing the difference between a scalar, like distance, and a vector, like displacement, we are finally ready for the main event. Let's settle the score between speed and velocity once and for all. And it connects perfectly. Speed is the scalar. Why? Because it's based on distance, our scalar measurement, divided by time. Speed only cares about how fast your odometer is ticking up. Velocity, well, that's our vector. It's calculated using displacement, our vector measurement. It tells you how quickly your position is changing and in what direction. Now, to really make this stick, let's use a fantastic example that can feel a little bit like a brain teaser at first. Imagine a race car on a 3-kilometer circular track. It starts at the finish line, and it completes exactly one perfect lap, ending right back where it began. Now, this car is moving fast. It has traveled a distance of 3 kilometers in a very short amount of time. If you calculate its average speed, that's distance divided by time, you're going to get a big number. Let's say it's 180 kilometers per hour. There is no question that car has a very high speed. But here's the million-dollar question. We know its average speed is super high. But what is its average velocity for that entire complete lap? Think about what we just learned. Before you answer, just remember the rule. Velocity isn't about the path taken. It's all about displacement, the straight line change in position from your starting point to your finishing point. The answer is a big fat 0. Its average velocity is 0 kilometers per hour. How is that possible? Well, after one full lap, where did the car end up? In the exact same spot it started. Its start and end points are identical. That means its total displacement is 0, and 0 divided by any amount of time is always 0. So let's wrap all this up. It's a neat little distinction, but is it just some weird physics trivia question? Absolutely not. Understanding this difference is incredibly important in the real world. Here's the whole thing in a nutshell. Distance is your scalar, just the total path. Displacement is your vector, the change from start to finish. That makes speed the scalar that measures how fast you're moving, and velocity the vector that measures the rate your position is changing. It all links together. And why should you care? Well, think about it. An airline pilot can't just know their speed. They need to know their velocity, speed, and direction to get you to your destination. An astronomer calculating the orbit of a planet needs its velocity, not just its speed. Anytime direction matters, velocity is what you need. So I'll leave you with this to think about. We've seen how just adding direction totally transforms speed into velocity. Where else in your life does adding a direction, a goal, a focus, completely change the meaning of what you're measuring? Something to chew on. Thanks for joining me.